Hi, welcome back to the series of lectures on major theory with course code MDC 202. Hope you all are fine. Today, in this lecture, we will prove Steinhauss theorem. So, in this lecture, we will discuss Steinhauss theorem. Steinhauss theorem. Steinhauss theorem actually states that given a subset E of Rn such that the Lebesgue measure of E is positive, then I can find delta. Then I can find delta such that this interval n times, it's a subset of Rn actually. This is a bounded upper interval of Rn. This interval is subset of E minus E. That's the algebraic difference of set E. Okay, so it states that if it is a subset of Rn and its Lebesgue measure is positive, then I can find delta such that this bounded upper interval of Rn is subset of E minus E. Even if it is also subset of Rn because E is subset of Rn. So to prove this theorem, we first prove the following lemma. Then we state Steinhauss theorem. Okay. To prove Steinhauss theorem, to prove the Steinhauss theorem, we first prove the following lemma. We first prove the following lemma. Lemma is let E be a subset of Rn. Let E be a subset of Rn. Subset of Rn such that Lebesgue measure of E is positive. Such that Lebesgue measure of E is positive. Then for each epsilon 0 less than epsilon less than 1, then for each 0 less than epsilon less than 1, then for each epsilon which lies between 0 and 1, there exists a bounded upper interval I of Rn. There exists a bounded open interval of Rn such that epsilon times Lebesgue measure of I is less than lambda Lebesgue measure of E intersection I. You can easily illustrate this theorem for one-dimensional space. You fix some subset E of R with Lebesgue measure positive. You fix some interval, then you choose any epsilon positive. You can see you will always find such interval I such that epsilon times Lebesgue measure of I is less than. So you do it yourself for R, and make some and construct some example. Okay, take E, any subset of R which is having Lebesgue measure positive. Then choose epsilon, fix your epsilon, say choose epsilon equal to 1 by 2. You will see that you will find an upper interval, bounded upper interval I of R such that epsilon times Lebesgue measure of I is less than Lebesgue measure of E intersection I. Okay, so let's prove this case for Rn in general. Now we had to choose fix. We had to fix them. Fix 0 less than, let epsilon be any positive number lies between 0 and 1. Okay. And E be subset of. And E be a subset of. It's a subset of E be subset of R n. It's any subset of R n. It's not a measurable subset of R n. Any subset of R n, such that Lebesgue measure of E is positive. It's positive. Okay. Now we can assume that we can assume that Lebesgue measure of E is finite. Is finite. So now if it's not finite, we can replace this by the other subset of R n having Lebesgue measure finite. So for this, if not, we define these sets. We define Bk, which is equal to the bounded. It's a bounded closed bounded subset of Rn. Actually, a ball with center at 0, with distance from 0 to x is less or equal to k, where k is any positive integer. So b1 is less or equal to 1, b2 less or equal to 2, and so on and so forth. Then you can see this. Then this Rn is actually the union, and k runs from 1 to infinity Vk. It's like if you take a real line R, then this real line R is the union of the intervals minus n to plus n, where n runs from 1 to infinity. So this is the case for Rn. Rn is equal to union k runs from 1 to. You can easily verify. Let's choose any x belongs to R, and then x must be in some ball. X must be in some ball with center at 0 and certain radius, certain some positive integer, some radius. So it's in some ball, and each ball is subset of R, and therefore union is subset of R. So that's simple actually. This Rn is subset of that union. So this implies, but E is actually equal to E intersection Rn. Okay, that's equal to E intersection union k runs from 1 to infinity Bk, and which is equal to union k runs from 1 to infinity E intersection Bk. Okay, so that implies since E is the union, therefore each set in this union is subset. So this implies E intersection Bk is subset of E for all k greater or equal to 1. And this Lebesgue measure of E intersection Bk is less or equal to Lebesgue measure of Bk. That's the monotone property. And this is closed bounded ball with center at 0. Therefore, this is finite. This Lebesgue measure is finite. So that means Lebesgue measure of E intersection Bk is finite. Now we replace E by E intersection Bk. We show that if the result is true for E intersection Bk with Lebesgue measure finite, then it's also true for E. Now, and suppose result holds for E intersection Bk. So then there exists a bounded open interval I of Rn such that epsilon times Lebesgue measure of I Lebesgue measure of I is less than Lebesgue measure of what's the set? Set is here E intersection BK and intersection I, and this is obviously less or equal to Lebesgue measure of E intersection I. So therefore result also holds for E, because epsilon times Lebesgue measure of I is also less than Lebesgue measure of E intersection I. Therefore result also holds for E. So whenever result is true for any Lebesgue measurable subset E intersection Bk of Rn having Lebesgue measure finite, then it is also true for this Lebesgue measurable subset E of Rn having Lebesgue measure not finite. So therefore we can assume that the Lebesgue measure of E is finite, because if we prove the result for those subsets of Rn having finite measure, then it is true for any subset of Rn. Okay. So thus we can assume that thus we can assume that Lebesgue measure of E is finite. Okay? Because if it is true for the set subset of Rn having finite measure, then it is true for any subset of Rn. Obviously of non-negative measure. Okay. So we can assume that this Lebesgue measure of E is finite. So again, since 0 less than epsilon less than 1, then we can find that there exists a sequence II. There exists a sequence II of bounded open intervals, of bounded open intervals of Rn, such that E subset of union I runs from 1 to infinity, and epsilon times Lebesgue measure of the union. Sorry, it's a summation. It's a summation, not the union. This is the bounded sequence such that the Lebesgue, this summation I runs from 1 to infinity. Lebesgue measure of I is less than Lebesgue measure of E. This can be done. This can be done. You can find a sequence. Suppose that there is no such sequence. For if possible, there is no such sequence. Or if possible, there is no such sequence. There is no such sequence. Then any such sequence II are bound open interval with E subset of this union. This the reverse inequality holds. Then, because we don't have a sequence of this type having satisfying this property, so then for any sequence II of bounded open intervals such that a subset of union I runs from 1 to infinity, and this epsilon times summation I runs from 1 to infinity, Lebesgue measure of I is less or equal to Lebesgue measure of E. So let's take the infimum over those sequences, because it's true for any sequence. This implies epsilon times infimum of the summation I runs from 1 to infinity, Lebesgue measure of I, where I is bounded sequence and E is subset of union I is less or equal to Lebesgue measure of E. But this, by definition, this it is already done that this is equal to actually Lebesgue measure of E, which implies epsilon times Lebesgue measure of E. It has already been explained is less or equal to Lebesgue measure of E, which implies epsilon is greater or equal to 1, which is a contradiction because epsilon is less than 1, a contradiction. A contradiction. Okay, that's we have a sequence. That's there exists a sequence I of bounded open intervals, bounded open intervals of Rn such that this holds epsilon times summation I runs from 1 to infinity. Lebesgue measure of I is less than Lebesgue measure of E. Lebesgue measure of E. Now to complete the proof, because we have to find some interval I, to complete the proof, we show that there exists I such that Lebesgue measure of E intersection I it's less or equal to Lebesgue measure of E. It's less or equal to epsilon times it's less or equal to epsilon times this epsilon times Lebesgue measure of I. So we show that there exists some bounded open interval I such that Lebesgue measure of E intersection I is less or equal to epsilon times Lebesgue measure of I. So this is actually what we need to prove. Actually, you can see the statement of lemma here. What's the statement of lemma? For each epsilon positive, there should exist so that epsilon times Lebesgue measure of I is less than Lebesgue measure of E intersection I. Okay, Lebesgue measure of E intersection I. This epsilon times actually we show that this one. We show that this is not correct here. We show that this one. We show that epsilon times there is I such that epsilon times Lebesgue measure of I is less than Lebesgue measure of E intersection I. That's what we need to prove actually. There exists some bounded interval I of Rn such that epsilon times Lebesgue measure of I is less than Lebesgue measure of E intersection I, and that bound open interval is I. So we find there is for certain I this holds. So there exists some bounded open interval I. Now if not, then the reverse inequality will hold for each I. Then Lebesgue measure of E intersection I, then Lebesgue measure of E intersection I is less or equal to epsilon times Lebesgue measure of I. So this is the case. If it's not true for some I, then the reverse inequality hold for all I greater or equal to 1. Now we find contradiction. Now Lebesgue measure of E, which is equal to Lebesgue measure of E intersection union I runs from 1 to infinity I, because E is subset of this union, and which is equal to Lebesgue measure of the union I runs from 1 to infinity E intersection I. Okay, now you can apply this subadditive property. You can apply the subadditive property about Rho is less or equal to summation I runs from 1 to infinity Lebesgue measure of E intersection I. Okay, and but this is true for this is less or equal to epsilon for each I, so it's less or equal to epsilon times summation I runs from 1 to infinity Lebesgue measure of I, but this sequence is chosen such a way that this epsilon times summation I runs from 1 to infinity Lebesgue measure of I is less than Lebesgue measure of E. So this is no contradiction. Okay, this is Lebesgue measure of E, and it ends with Lebesgue measure of E. So where we have a strict inequality, so therefore this is a contradiction. Okay. Here we have the subadditive property. Then the Lebesgue measure of E intersection I is less or equal to epsilon times Lebesgue measure of I. So that's here. Lebesgue measure of E intersection I is less or equal to Lebesgue measure of I, and this one epsilon times summation of this is less than Lebesgue measure of E. That's here. That's here. Okay. Epsilon times this is less than Lebesgue measure of E. Okay. So which implies Lebesgue measure of E is less than Lebesgue measure of E, a contradiction. A contradiction as required. As required. Thus we have such a bounded open interval. Okay. So that proves the lemma completely. Next we prove our main theorem, that's Steinhauss theorem. Okay. Steinhauss theorem. Steinhauss theorem. So the statement is let if E is a Lebesgue measurable subset, if A is a Lebesgue, if he is a Lebesgue measurable subset of Rn such that Lebesgue measure of E is positive. So in the previous lemma, E was not measurable, but here the E is measurable, and also its Lebesgue measure is positive. Then zero vector is interior point of E minus E means then zero vector. It is because we are in Rn, so the elements, the points of Rn are called vectors. Okay, then zero vector of Rn is an interior point of E minus E, or we can say interior means, or we can say there exists a bounded open interval, bounded open interval I of Rn containing zero, containing zero. So zero is neighborhood of I. So there is a bounded open interval I containing zero, such that I is subset of E minus I. That means this zero is actually interior point of E minus E. Okay, so let's prove this theorem. So proof of the theorem. Proof. Okay, proof. Assume E is measurable if Lebesgue measure of E is positive. That's our assumption. That's in the statement. Assume E is measurable and its Lebesgue measure is positive. So since Lebesgue measure is positive by previous lemma, for each epsilon 0 less than epsilon less than 1, we can find bounded open interval. So let's choose this epsilon. Choose epsilon for for epsilon equal to 3/4, which lies between 0 and 1, we can choose a bounded open interval I, which is equal to I runs from 1 to n. This product of the n copies of bounded intervals of I R. Okay, this I is bounded open interval of Rn means it's equal to the product of n copies of bounded open interval of R. So this is bounded open interval of Rn such that choose by previous lemma, okay, by lemma, which we have already done. By lemma, choose a bounded open interval I of Rn such that this epsilon times epsilon is here 3/4 times Lebesgue measure of I. Lebesgue measure of I is less than Lebesgue measure of E intersection I. Lebesgue measure of E intersection I. Next, choose delta positive. Now, so let me write first this one. Now this Lebesgue measure of I is obviously less than 3/2 times Lebesgue measure of I, or that's equal to Lebesgue measure of 3/2 times I, okay? Because 3/2 is greater than 1. So therefore I can choose delta so small, choose delta positive so small such that we define the interval I delta, which is the product of again n copies, but these intervals are bigger than the intervals ai bi, because we are subtracting delta from left side and adding delta on the right hand side. Okay, so this length is obviously greater than the length of this interval is obviously greater than the length of the interval I, but we choose delta so small, still this length, since this Lebesgue measure of I is strictly less than Lebesgue measure of 3/2 I, so we choose delta so small such that Lebesgue measure of I delta will be strictly less than Lebesgue measure of 3/2 times I. This can be done and satisfying Lebesgue measure of I delta is strictly less than 3/2 times Lebesgue measure of I. Okay. And obviously this Lebesgue measure of I is less than, actually this Lebesgue measure of I is less than 3/2 times Lebesgue measure of I. So we choose delta so small. So this Lebesgue measure of I delta is greater than Lebesgue measure of I. It is plus some quantity, but that quantity is so small such that Lebesgue measure of I delta is still less than 3/2 times Lebesgue measure of I. Okay, and then we consider the interval. Consider the bounded open interval J, which is equal to minus delta plus delta cross minus delta plus delta cross n times. Okay. Consider the bounded open interval this of Rn. This delta is already defined. Okay. Okay. Now to complete the proof, we show that obviously this 0 belongs to J, because 0 vector belongs, because 0 is here, 0 is here, so 0 that n tuple 0 vector, it belongs to J. So obviously the 0 vector belongs to J. So to complete the proof of the theorem, complete the proof of the theorem. To complete the proof of the theorem, we show that this J is subset of E minus E. E minus E. So that means zero vector is interior point of E minus E. So let X belongs to, so let's take X belongs to G. G. Okay, then this one, E intersection I, then its union with X plus E intersection I. Okay, it's obviously subset of this. E intersection I is subset of I. It is subset of I. This is subset of X plus I. Okay, this one it's subset of union X plus I. But since this X is chosen in this interval J, that means each coordinate of this vector, x1, x2 up to xn, each coordinate of this vector lies between minus delta and plus delta. Then you can easily verify this I union X plus X. I is obviously subset of I delta, but X plus I is also subset of X. This I delta, I is subset of I delta. X plus I is also subset of I delta. Why? Because this X is in this set. Each coordinate of the vector lies between minus delta and plus delta. So this is obviously subset of I delta union I delta. This is also subset of I delta, which is equal to I delta. So this union, it's here union, okay? This union E intersection I union X plus E intersection I is subset of I delta. This implies Lebesgue measure of this union E intersection I union X plus E intersection I, this one is less or equal to Lebesgue measure of I delta. Okay, and this Lebesgue measure of I delta is less than 3/2 times Lebesgue measure of I. So let's this name as star. Now, we claim that these two sets are disjoint. These two sets are not disjoint with each other. Now we claim that E intersection I intersection X plus E intersection I is not equal to 5. Okay, for if E intersection I intersection X plus E intersection I is the empty set. Since both are the measurable sets, E is measurable, I is measurable. So this intersection is measurable, and X plus E intersection I is also measurable, and they are disjoint sets. We can apply the additive property of Lebesgue measure on measurable sets. So then Lebesgue measure of E intersection I union this X plus E intersection I is obviously it's equal to, using additive property, Lebesgue measure of E intersection I plus Lebesgue measure of X plus E intersection I. But we know that Lebesgue measure is translation invariant. So this is equal to Lebesgue measure of E intersection I plus this one, Lebesgue measure of E intersection I, because Lebesgue measure is translation invariant, and that's equal to 2i's Lebesgue measure of E intersection I. 2i's. But this Lebesgue measure of E intersection I is greater than 3/4 times. So this is now 2i's. This is greater than 2 times, and 2i's 3/4 times Lebesgue measure of Lebesgue measure of this I, Lebesgue measure of I, and that's equal to 2 by 3 times Lebesgue measure of I. So thus a Lebesgue measure of the union is greater than 2 by 3 times the Lebesgue measure of I. But here from star, Lebesgue measure of the union is less than 3 by 2 times the Lebesgue measure of I. So there is this is a contradiction. So this is a contradiction, a contradiction, a contradiction, a contradiction. So thus they are not disjoint. Thus E intersection I intersection x plus E intersection I is not equal to the empty set. So let's choose some point. Let's choose some point in the intersection. So let's choose some point. So let's choose this point. Choose y belongs to E intersection I and y belongs to x plus E intersection I. Y belongs to E intersection I. So this means y belongs to E. Y belongs to E. And this y is equal to some x plus z, where this z is also in E. Because it's x plus the point of the intersection, where this z also belongs to E, where this z belongs to E, where z belongs to E. So which implies this x is equal to y minus z, which implies x is equal to y minus z, where y belongs to E, z belongs to E. So but y minus z, it belongs to E minus, because it is the algebraic difference, E minus E. E minus E means the set A minus B such that A, B both belongs to its set of all such points. And here y and z, they are in E, therefore this y minus z, it belongs to E minus E. So thus our J, because x was chosen in J, thus J is subset of E minus E. And hence the theorem follows. And hence the theorem follows. So in next lecture, we will prove Ostrovsky's theorem, which gives the measurable solution of the function f of x plus y equal to fx plus fy. That's in the next theorem. Thank you.